Your A game. Here we go. Rotary motion. There are two types of velocities. Okay. At this level, at this moment, there's two types of velocities. We got something that's an angular velocity and something that's a linear velocity. Angular velocity, guys, is just how fast something spins or rotates. How fast, quote unquote, something rotates slash spins. You know what? I shouldn't use the splash because you guys might think that's per. Rotates or spins. So think of like, what are possible units? Let me put the word possible units. Possible units. Possible units could be like radians per second, revolutions per minute or second, um, degrees per minute, any type of rotational, anything that rotates per unit of time. So it doesn't have to be per second. It can be per minute. It can be per hour. Radians per second, radians per minute, radians per hour. Revolutions per minute, revolutions per second, revolutions per hour. Degrees per minute, degrees per second, degrees per hour. Are we okay with that? Okay. And linear velocity is distance divided by time. So what are possible units for that? Possible units for linear velocity. Meters per second, miles per hour, kilometers per minute, kilometers per hour. Anything that has to do with distance divided by time. Centimeters per second. Does that make sense, guys? Nothing crazy, right? You guys okay? Okay. All right, and then here are some formulas or some symbols. R is always going to stand for radius. A in this case, number of units of arc length. So that's going to be this distance right here. That's going to be in centimeters or whatever, inches or whatever. Theta, bless you. That's an angle. Sometimes in radians, sometimes in degrees. Sometimes it's a revolution, like one revolution or whatever. V always stands for linear velocity or velocity. This is an omega, and it's an angular velocity, so that's like this rotational velocity. And then T stands for time. There are formulas. See, there's some formulas here. If you go to the next page, you'll see some more formulas, guys. But look, I'm not going to reference the formulas. You're going to try it my way first. And then if you don't like it my way after 2 days, then yes, I'll just give you some formulas and then just do it with the formulas. Cool? All right. When you see a radian, I guess I pushed the arrow by accident. Delete. When you see the word radian, it literally means radius. So that's what it means. 1 radian is whatever your radius is. So that's why sometimes they call the radian unit unitless, because it depends on what unit you're using for your radius. All right, you guys ready? Here we go, guys. Example 1. It says, an old LP long play record, as in the figure to the right, rotates at 33 1/3 revolution per minute. You know what? I'll make sure the next time I put it right here. I guess it didn't fit. Revolutions per minute. Okay. Find the angular velocity in radians per second. Well, this already is an angular velocity, but that's in revolutions per minute. They don't want revolutions per minute. They want radians per second. So here's how we're going to do it. Have you guys heard of the T-chart? So you're going to go 33 1/3, and you're going to write rev in the top, and you're going to do a T, like a little T, and you're going to put the word minute in the bottom. Do you guys remember this from chemistry? And here's what I want to do. I want to cancel the word revolution. So I'm going to write a revolution right here. And I need to find a relationship between a revolution and a radian. Well, in 1 revolution, how many radians are there? 2 what? Yeah, 2 pi. So write 2 pi radians or 2 pi rad. And there it is. The revolutions cancel out. Look, I have a revolution on the top. I have a revolution on the bottom. They cancel out. So the way this works, this is like a long fraction. I'm going to keep going. Radians per minute. Is that what I want? What do I want? Radians per second. So I want to cancel the minute. So I'm going to write a minute in the top. and I'll make a relationship between minutes and seconds. I'm going to write second in the bottom, and in 1 minute, how many seconds are there? So the way this works, guys, this is like a big fraction. So you're going to multiply whatever's in the numerator together, and then you're going to divide by whatever you have in the denominator together. And you're going to multiply everything in the denominator. Obviously, in the denominator, you just got 1 times 1 times 60. So you're going to take your calculator. So everyone, get your calculator, guys. This is why I told you guys to reset it, because there's a lot of junk in there. So you're going to do it like this, always and always and always. Put a fraction in there. Push alpha, y equals, and then push enter. Does everyone have a fraction? Okay. Chab, I don't know how to answer that 33 1/3. Let me show you. So in the numerator, push alpha again. Push the y equals, and look, push the number 2. See, U-N-D. Push number 2, or scroll down and push 2. And the third is, see, put 33 1/3, like so. And then I'm going to move to the right. I'm going to go times. And then this says times 2 pi. So I'll put the 2 pi on the top. And the pi is next to the little caret. You got to push the second button and the caret. And then in the bottom, I'm going to put 1 times 1 times 60. You don't need to put the 1. You can just put times 60. And then push enter. And voila. And there it is. 3.49065. At least how many digits after the decimal? Yeah, at least 3, but the more the merrier. 4 is even better. So I'm going to write 3.49. I already forgot short-term memory. 06585. 06585. And put units. The only thing I have left is radians per second. There it is, guys. I guess you can also leave it in terms of pi, but for now, we're just going to worry about typing stuff into the calculator. How do we feel right now, guys? Are we okay? All right, let's keep going. Find the angular and linear velocities of the record per second at the point at which the needle is located when it is just starting to play 14.5 centimeters from the center. Okay, so way over here, do you guys see this record? Have you guys seen a record before? The minor records before? Okay, when it's spinning, I want to know how fast it is spinning, the linear velocity in centimeters per second. That's linear velocity. What else do they want? They want angular velocity. Okay, this radian, it doesn't matter where you're at. You're going to be spinning that fast in radians per second everywhere you're at. That's a rotational. Doesn't matter where you're at. You can be over here. You can be a bug there. You can be a bug here. You can be a bug there. That's how fast you're spinning. You're going to be spinning that speed, the angular velocity, no matter what. So my angular, I'm going to write omega equals 3.490655 radians per second. And this is everywhere. Everywhere on the record. Everywhere on record. Bless you. Oh, Leonie. Okay. What's up, miss?
What is the omega?
It just means omega is just used to indicate angular velocity. How fast it's spinning. It's spinning that fast. They want the linear velocity. Here's what you're going to do. Let's do a T-chart. 3.490655 radians per second. And remember what I told you, a radian is my radius. So in 1 radian, what's my radius? Yeah, say it aloud, guys. What's my radian? What's my radius? 14.5. 14.5 centimeters. Look, radians cancel out. And I have centimeters per second, and that's what I want for linear velocity per second. So I come to my calculator. You don't have to do the T thing. You can just go this number. So scroll up, enter. Or actually, you can just type, it's still there. Let's scroll up. Yeah, it's still there. You can just type enter, watch. Or times, there it is, answer. Times 14.5. Times 14.5, enter. And there it is, 50.61454. 50 point, I already forgot it. 61454. 61454. And I need units. Centimeters per second. How are we feeling so far? Okay. Check it out, guys. Let's see if we're going to get tricked. At the point at which the needle is located when it's just starting from the center. Okay, yeah. Letter C. Find the angular and linear velocities per second at the center of the turntable. The angular velocity, this is spinning at at this rate, 3.4906585 radians per second, everywhere on the record. It doesn't matter. Center, here, at the edge of that. So my angular velocity is the same everywhere. 3.4906585 radians per second. Okay, the linear velocity. Imagine, this is a bird's eye view. If you're in the center, my linear velocity, are you traveling any distance? No, you're just, if you're in the center of that turntable, you're just spinning. You're not traveling any distance. See, if you're on the edge, oh, I got dizzy there. If you're on the edge, then yeah, you're traveling this whole distance on the outside, on the exterior. You're traveling that whole circumference. But if you're right smack in the middle, you're just spinning. You're not traveling any distance. You're not going through that arc. Do you guys see that? So what's your linear velocity if you're in the middle? 0. And put units. This is actually the one that you can put any unit you want. It'll be correct. 0 miles per hour, 0 kilometers per second, 0 centimeters per second, because you're not moving. As long as it's distance divided by time. Okay, how do we feel, guys? Was that exciting? Maybe not, because it was just a record player. All right, look. Has everyone ridden a bike before? Do you guys know what a bike is? Okay. I'm going to go slow. And I know it's late, guys, but let's see. Hang in there. All right, check out this bicycle problem. The figure to the left shows the back wheel of a bicycle. A small sprocket is connected to the axle of the wheel. This sprocket is connected by a chain to the large sprocket to the wheel, to the large sprocket to which the pedals are attached. So there are several rotating objects whose motions are related to each other. Let's dig in. Ready? A cyclist turns the pedal of her bicycles at 8 radians per second. So I'm going to zoom in. So I'm pushing those pedals at 8 radians per second. How many revolutions is that, Chav? I don't know, divided by 2 pi. 1 revolution is 2 pi. Bless you. 1 revolution is 2 pi radians. Are we still okay, guys? All right. The front sprocket has a diameter of 20 centimeters. Okay, if the diameter is 20 centimeters, that means the radius is 10. R equals 10 centimeters. And it's connected by the chain to the back sprocket. Yeah, I see that. Which has a diameter of 6 centimeters. Okay, here's my back sprocket. If the diameter is 6, that means the radius is 3. Are we still okay? Okay, which has the rear wheel has a radius of 35 centimeters and it's connected to the back sprocket. Okay, rear wheel, 35 centimeters. I love it. Oh, man. Is that relatively straight? Are we okay so far, guys? Okay. What is the angular velocity of the front sprocket? It's not a trick question. Here's my front sprocket. This is that's angular velocity right there. What is it? Yeah, they didn't tell me what units to use. I'm just going to use that one. 8 radians per second. I could have done it in revolutions if I wanted to, but they didn't tell me that, so I'm just going to leave it alone. Don't do more work than necessary. Are we okay? Nothing crazy, right? What do you think, Volpert? Not bad? Okay, here we go. What is the linear velocity of points on the chain? Okay, they want the linear velocity of points on this chain. Well, I take my angular velocity. So I'm going to go 8 radians per second. Do a little T-chart. And what's my radius of that front sprocket? So I'm going to go in 1 radian. Remember that radian means radius. There's 10 centimeters. The radians cancel out. 8 times 10 is 80. 80 centimeters per second. There it is. That's my linear velocity. How are we feeling right now, guys? Are we feeling okay? What do you think of that? Okay, what's up, Henderson? Hit me.
Oh, okay. Just like how did based on the question, how did you know like those were the measurements you had to use like?
Oh, because the chain is dictated by the front sprocket, the speed of the chain. And see, I'm connected to that. So I have to use my radius of the front sprocket for that one because that's where, see, I'm pedaling this. So, and that's connected to the chain. So there it is. So I have to use the front one. Does that make sense?
Yes. And then what's it called? And so the linear velocity,
Yeah, that's how fast that, if that chain were to be touching the ground, you would be going 10 centimeters per second. That chain is, that's the speed of the chain. You know, or if you were able to ride that little front sprocket somehow, you would be going at 10 centimeters a second. I know that's so weird to say because, you know, you don't ride a front sprocket, but yeah. You know what I mean? Are we okay? Okay. I'll put an awkward emoji on this for the analogy of the front sprocket riding it. Like, no, okay, I'll stop. You know what? I'm just going to delete this conversation right here. Okay, but we're good, right? Okay. Are we okay so far? All right. What is the linear velocity of points on the rim of the back sprocket? Okay, so let me zoom in. They want to know what's the linear velocity of points on the rim on the back sprocket. So these blue dots right here. What's the linear velocity of that back sprocket there? Take a guess. I don't know, Chav. I'm just started this. I don't know. It's late. The class is it. What is it? No. How fast is the chain moving in the front sprocket? What's my linear velocity of the front sprocket? 80. And isn't the back sprocket connected by a chain? So what's the linear velocity of the back sprocket? What is it? 80. Yeah, 80. Why is it 80 centimeters per second? It's connected. If the chain, okay, it better be going 80 centimeters per second in the back sprocket, because if not, that chain is coming off. Guys, it's going 80 centimeters per second in the front, so it has to be going 80 centimeters per second in the back. Do you guys see that? So it must be the same. So I'm going to write, what is the linear velocity of points on the, I'm going to write same, comma, since chain is connected to front sprocket, comma, what is the linear velocity of points on the rim of the back sprocket? Linear velocity of back sprocket must be 80 centimeters per second. Same, since the chain is connected to the front sprocket, linear velocity of back sprocket must be 80 centimeters per second. The chain is also connected to the back sprocket. You should say that somewhere. The chain is connected to the front and back sprocket. The chain in the front is going 80 centimeters per second, so it has to be going 80 centimeters per second in the back. Does that make sense, guys? Okay, let's go to the next question. All right, bless you. What is the angular velocity of the center of the back sprocket? They want to know how fast it's spinning. Okay, well, I know my linear velocity. My linear velocity is what? So I'm going to take the 80 centimeters per second. And this time, I'm looking at the back sprocket. And this time, I'm going to say, okay, the back sprocket, it's definitely spinning faster than the front sprocket. What's my radius of the back sprocket? So I'm going to come back and I'm going to say, in 3 centimeters, there is 1 radian. And look, there it is. Now I get radians per second. Do you guys see that? So I take the 80, and I'm going to go 80, and I'm going to divide it by 3. 26.66667. Oh, let's not say 26.667. We want to go to heaven. Radian. No. Hey, stop. We want to go to heaven. No. Okay. Okay. Put your pencils down, guys, because I don't. Sometimes I feel like. All right. I just want to talk real quick about this. This is not the only way, guys. If you know what you're doing, if you 100% know what you're doing, look. Have we even talked about any formulas? We've been doing everything with dimensional analysis. You could have done this question differently. Look, just listen, just take this in, observe, watch. You could have said, Chav, I know the angular velocity of the front sprocket. They gave it to me. That was 8 radians per second. Do you guys see that? So you could have said this. You could have said If the front sprocket is going 8 radians per second, and the front sprocket is connected to the back sprocket, I can just make a ratio. This front sprocket, I forgot what was it, 10 centimeters, and this back sprocket is 3 centimeters. So if I make a ratio from the front sprocket to the back sprocket, look at this, 10 divided by 3. So what does that mean? 3.333. This is what it means. Every time the front sprocket does 1 revolution, the back one does 3.333 revolutions. Does that make sense, guys? So look, I could have taken that 8, multiplied it by 3.333, and I bet you we're going to get the same answer digit per digit. Look at this. Look at this. You see that ratio? Times 8, because it's 8 radians per second in the front. So how fast is the back sprocket going? Look at that. 26.6667. Do you guys see what's going on? If you know what's going on, and look, we haven't even used a single formula. If you know what's going on, if you know how to manipulate the variables, guys, this is how you can do all your physics and chemistry classes, all of them. You can do it like this. Anything that has to do with dimensional analysis, you can always analyze it like this, and you'll always be right. So I hope that not breaking, but I hope that you guys are opening up your minds, like, oh, okay, you can just analyze the dimensions or the units, and if you know where you're going, you can just manipulate it till you get an answer that you need. Does that make sense, guys? Okay, you can write that down now. I guess I'll write it for you if you need it. I'm going to write it in different colors. You can also use geometry. Find ratio of circles. 10 divided by 3, which equals 3.333. And then multiply. Multi. So 8 times 3.333 equals 26.667 radians per second. Are you not entertained? Yes. I'll look at it right now, miss. Right now we're doing this. Okay. I thought you had a question about this. Okay. No, we're good. All right. How are we feeling, guys? All right. Last question, and then we'll do a question together on rotary motion. How fast is a bicycle going in kilometers per hour? Well, okay. Before we can answer that question, you gotta at least, hopefully we know. Has everyone ridden a bike? All right. If the back sprocket does 1 revolution, when you're spinning it, then the wheel does 1 revolution. Does that make sense to you? So the back wheel and the back sprocket have the same what? Angular or linear? Angular. They both have the same angular velocity, guys, because they share an axle. So if this back sprocket goes 1 revolution, the back wheel does 1 revolution. Does that make sense, guys? All right, so here we go. I'm going to take my angular velocity that I have here. So I'm going to go 26.667 radians per second. And now we're doing the back wheel, guys. In 1 radian, how many centimeters are there for the back wheel? 35. So that's what you're going to put. In 1 radian, there's 35 centimeters. Okay, the radians cancel out. Right now I have centimeters per second. Is that what I want? No, I want kilometers an hour. Ooh, do you guys know the metric system? Yeah, sure we do, right? Kilo, hecto, deca, base, deci, centi, milli. No? Never? Okay, time out. Guys, before we graduate, you're going to be at the university with some students who have been doing the metric system since they were 4 or 5, because some are coming from other countries. The whole world uses the metric system. So before we graduate, we got at least, if you can know micro, pico, all those, even great, but at least know these: kilo, hecto, deca, base, deci, centi, milli. The kilometer is bigger than a centimeter, obviously. So 1 kilometer equals, well, Chav, how do I figure it out? Okay, well, here it is. Ready? Here's a kilometer, and I'm going to count all the way until I get to centimeters. 1, 2, 3, 4, 5. Do you see what I did there, guys? So that's how many zeros I'm going to add. Here's my 1. 1, 2, 3, 4, 5, and then I put cm. So there is 100,000 centimeters in 1 kilometer. Make sure you know this. This is what is this called? This right here starts with an M. The metric system. It goes by base 10 each one. So make sure we know you've seen it before. Where have you seen it? 7th grade maybe, biology, or you've seen it. I guarantee you've seen it. So get really good. All right, here we go. I'm gonna write 100,000 centimeters down here, and I'm gonna put 1 kilometer. So there it is. The centimeters cancel. So right now I have kilometers per second. Is that what I want? No, 1 kilometers per hour. So I'm gonna write 60 seconds. I guess. Well, I already wrote it. So too bad. I was gonna try and do it in one move, but in 60 seconds, there's in 1 minute there's 60 seconds, and I'm gonna cancel the minutes. So I'm gonna write 60 minutes, and I'm gonna write 1 hour. So notice, look, minutes cancel out, seconds cancel out, and the only thing I have left is kilometers per hour. This is like a big fraction. You're going to be multiplying 26.667 times 35 times 60 times 60. And on the bottom, just 100,000, it looks like. So I take my calculator. I'm going to push alpha y equals enter. Get my little fraction. And make sure to always get that little fraction. 26.667. 26.6666667 times 35 times 60 times 60. If you want to type 60 squared, go ahead. If you want to, push less buttons, divided by 100,000. 100,000. Enter. There it is. Hopefully you got that as well. 33.6 kilometers per hour. I think that's about 20 miles an hour. It's pretty fast. I guess we can ask Google real quick, see how fast that is. 33.6 kilometers per hour to miles per hour. 20 miles an hour. So that's pretty good speed for a bike. Yeah, make sure you verify, guys. When I ask this question sometimes on the exam, you guys tell me they're going like 3 billion miles an hour. Guys, make sure, come on, guys. Who's this person? Superwoman? 3 billion miles an hour? Come on, LOL. All right, one more. Go to activity 9. Has anyone in here ever mowed the lawn before? Have you ever wondered how fast a rock is coming out of the lawnmower when the blade hits it? When you mowed the lawn, you never hit like an object and you saw the rock just fly? Yeah. All right, well, we're about to find out. All right, we're all going to go to number 2. Go to number 2. So let's see what this says. The blade on a rotary lawnmower is 19 inches long. That's about standard size, guys, for the low-end lawnmowers. That's the standard size. The cutting edge begins 6 inches from the center of the blade. So if you're right, in order for a lawnmower blade to cut grass, it must strike the grass at a speed of at least 900 inches per second. Is that 900 inches per second angular or linear velocity? Linear. It's distance divided by time, so it's distance. It's linear. Angular is anything to do with rotation. Cool? Radians, revolutions, degrees. Okay. All right. Letter A. If you want the innermost part of the cutting edge, this is a safe space. It's all good. If you want the innermost part of the cutting edge to cut grass, how many radians per second must the blade turn? How many revolutions per minute is this? Ooh, you know what? I just remembered. I don't think I answered that question, the second part for earlier, but we're gonna do it now. All right. So they're talking about this, the innermost part. They want to know that part right there. How fast that has to go in radians per second and in revolutions per minute to see. They just want to know. They want to know, like, to cut grass. All right. So what are we gonna start with? We're gonna start with what? We're gonna start with the 900. So write 900 inches per second. And here's my radius. What's the radius for that innermost? 6 inches. So we're going to write in 6 inches, there's 1 radian. See, first let's do the radians per second. So there it is. This is going to give me radians per second. Do you guys see that? So I take the 900 and I just divide it by 6. So 900 divided by 6. 150. So here it is. That's my first answer. 150 radians per second. So scratch out the, oh, no, I need the second. Scratch out the inches, and there it is, radians per second. Now I'm going to answer the second question. So I'm going to underline it in blue. How many revolutions per minute is this? Okay, well, let's take the 150. 150, bless you, radians per second. And how many radians in a revolution? 2 what? 2 pi. So write 2 pi radians. Radians cancel out. Use the fraction feature so you never mess up. So I'm going to use my fraction feature. And I'm going to go 150 in the top. And I'm going to put 2 pi in the bottom. And make sure everything's correct. Yep, everything looks good. And there it is. Oh, wait. Hold on. This is revolutions per second. Do I want revolutions per second? No. Okay, do one more line. And I want revolutions per minute. So I'm going to put what in the top and what in the bottom. Second and minute. The minute is longer. So in 1 minute, there is 60 seconds. All right, let's do it again. So I'm going to do it again, guys, from scratch. So I'm going to push alpha y equals, enter. And I'm going to go 150 times 60 divided by 2 pi. So I'm going to go 150. And I know I could have taken the other one, but I just want to be extra. 150 times 60 divided by 2 pi right here. And voila, there it is. 1,432. Wow, that's fast. 1,432.394488. 394488 revolutions per minute. Always put units. How are we feeling, guys? Are we feeling okay? All right, we're almost done. We're almost done. Letter B. What is the linear velocity of the outermost tip of the blade while it is turning, as in part A? Okay. It wants a linear velocity. I can actually use whichever one of these. I'm going to use the 1432 because I already have it in my calculator. So I'm going to start with that one. So I'm going to go 1432.394488 revolutions per minute. In 1 revolution, maybe I should have started with the radian one. Oh, well, too bad. I already started with this one. In 1 revolution, there's 2 pi radians. And in 1 radian, and let me slow down. What is the linear velocity? Underline the word outermost tip. So you're going to come over here. Here's the radius of the outermost tip, that distance. Well, I know that the diameter is 19. So the radius of that blue one there is 9.5 inches. Do you guys see that? The 19 divided by 2. Are we okay? So here we go. In 1 radian, there is 9.5 inches. Radians cancel. Revolutions cancel. This is my speed in inches per minute. So take the 1432, and everything in the denominator is a 1, so I can just multiply. 1432 times 2 pi times what? 9.5 times 9.5. And there it is, 85,500. 85,500 inches per minute. Oh, I needed the radius of the big one, of the outermost blade. So this is the diameter. I took 19 and divided by 2. All right, last one. Here's the big one. So today, guys, when you guys go home, tell your parents. Maybe your dad will be impressed. Like, Dad, I know how fast when a lawnmower strikes a rock, I know how fast it's coming out. Look, we're about to figure it out right now. If the outermost tip of the blade strikes a stone while it is turning, as in part A, how fast could the stone be propelled from the mower? How many miles per hour is this? All right, let's figure it out in miles per hour. Start with this because this is the speed of the outermost blade. So 85,500 inches per minute. And we're going to have to go to miles per hour. So we're going to have to go from inches to feet to miles. How many inches in a foot? In 12 inches, there's 1 foot. Ooh, let's see if we know this one. How many feet in a mile? In a test, I'll probably give it to you. But you guys have you guys seen a movie? Most of my facts I remember, I think, are coming from movies. Have you guys ever seen a movie called Remember the Titans? No? Okay, it's a movie with Denzel Washington about coaching football. And in one of the scenes, one of his players fumbles his football. And this is actually how I learned feeding them out. I'm not even kidding. I was a high school kid when I saw that movie. And he goes to this kid, his name was Petey, I think, and he goes, "How many feet are in a mile? How many feet are in a mile?" And he's like, "I don't know, coach." And like 5,280, and you're gonna run every single one of them, Petey. Something like that. I don't know. Google it and see what it says. So there is 5,000. Put this on the side. 5,280 feet in 1 mile. I also learned how fast the sunlight takes to reach Earth from a movie. How long does it take sunlight to reach Earth? Yeah, 8 minutes. I don't know a movie though. I can't remember, but I remember anytime little facts like that come out, I'm like, oh, cool. All right. Anyways, 5,280 feet in 1 mile. I'll probably give you that if there's an exam. So there it is. Feet cancel out, inches cancel out. So right now I have mile per minute. Is that what I want? No, I want miles per hour. So I'm going to cancel out the minute, put a minute in the top. Let's see, put an hour in the bottom. In 1 hour, how many minutes are there? There it is. Use the fraction feature. So I'm going to go alpha y equals enter. And I'm going to type. What am I going to type? 85,500. 85,500 times 60. And in the bottom, I'm going to type 12 times 5,280. This is all just one giant fraction, guys. Whatever you have in the bottom, you're multiplying together. Whatever you have in the top, you're multiplying the numerator together. Do you guys understand how to use this T-chart thing? Okay, you're not just saying that just to say that, like you really got it down? Okay. Have you done this before or no? Okay. Have you done Rotary Motion before? No? Don't you feel good that you can do these type of questions? Times 5,280. How fast is the rock going, guys? Did you guys already calculate it? Oh, okay. You see how when you get a fraction like that, just put a decimal in any one of them. So look, Chop, what do you mean? Just put a decimal anywhere. I'm going to put it right here. Dot. Bam. See? You can also tell the calculator. You could have also gone math decimal. 80.9659. 80.9659. And you need units. 9659. Miles per hour. Is that pretty fast for a rock? You think if a rock hits you at that speed that it would do some damage? So when you mow the lawn, put on protective gear, put on some sunglasses or some type of glasses, because if it hits your eye, guys, you say bye-bye to your eye. So tell your parents, like dad, mom, or grandpa, grandma, I know how fast a rock goes. If the lawnmower hits it, if the blade of the lawnmower hits it, it's going to go about 80 miles per hour. So please wear protective gear. All right. I just did all the notes and one of the questions from this activity. Do we feel like we have a good grasp? You got 45 minutes to do 3 questions. I think that's enough time to turn it in today. So that's it, guys. Just take care of business and we'll call it a day. So get it done and turn it in. And we'll continue this on Friday as well with another dosage of this. All right. That's it, guys.